Okay guys, we're back at it again. Hopefully all is well. We're doing an algorithm for sketching graphs of y equals f of x, so some general function. So again, we're putting this in a more formal aspect. We've already done the first derivative test. We've done the second derivative test. The first derivative test was to determine where the max and mins were, or potential max and mins, and the second derivative test was for the points of inflection. Now we're going to put everything we've learned from grade 12 advanced functions and calculus together in one super huge long algorithm. So just reading along. So step 1 says determine any discontinuities or limitations in the domain. For discontinuities, investigate function values on either side of the discontinuity. So if we look, you could have vertical asymptotes, so you'd want to know whether on the left and the right side, whether it was going to positive or negative infinity. Or if you could divide it out, you could get rid of the you could divide out any some discontinuities if there was a hole in your graph. So that's step 1. Step 2, determine any vertical asymptotes. We did that in grade 12 last semester. Determine any intercepts. You want x and y intercepts. Then you do the first derivative test, the second derivative tests. Then in step 6, test critical points to see whether they are local maxima or local minima, or whether it's a point of inflection or neither with the chart. Then determine the behavior of the function for large positive and large negative values of x. This will identify horizontal asymptotes if they exist. Then determine any oblique asymptotes, and then complete the sketch. Now up here it says note, as each piece of information is obtained, make use of it in building the sketch. Personally, I like to get all of the algebraic work out of the way, and then I can kind of look at the overall values and points that we have, and then I kind of know how big to make my scale to fit everything on it. So depends on what your preference is. So let's go and do the first example. Let's move down. So we are going to sketch this curve right here. So f of x is equal to e to the x times x squared minus 1. So again, discontinuities, there's going to be none. We have x is an element of real. We can sub any value of x in here. We can sub any value of x in here. So we're not going to have any discontinuities. So step 1's done and out of the way. Step 2, vertical asymptotes. It's not a rational function. I'm not going to have any vertical asymptotes. Let's move on to step 3. Now we get to the point where we're looking for x and y intercepts. So just take note of the form. X-intercept, set f of x equal to 0. So I do that right here. I have e to the x times x squared minus 1. I can factor that. It's a difference of squares, and I get this. And I pick up x is equal to negative 1 and positive 1 from this section. Right here, e to the x can never be 0, so I didn't have to write that down. For my y-intercept, set x equal to 0, and I end up getting negative 1, and I just do y-intercept is negative 1. Awesome, so some values are already coming out, and they're starting to look nice. Let's move down. Step 4, we're going to do the first derivative test. So just to make it nice, I wrote down what my function is. I took the derivative of that, and if you look, I have a function times a function, so I'm going to use product rule. Derivative of the first times the second plus the first times the derivative of the second. Notice how they both have an e to the x. I factor that out. I'm left with an x squared minus 1 plus 2x, and I just rearranged it so it looked pretty. Make sure you tell me what you're doing for this step. Set f prime of x equal to 0 for any critical values or critical points. So I set it equal to 0. This, again, cannot be equal to 0. E to the x can't be 0. So it's just this section that could be 0. So I'm going to do the quadratic formula on that because I can't find two numbers that multiply to negative 1 and add to 2 to factor it. Sub it into the quadratic formula, and I get this ugly decimal and this ugly decimal. And eventually I'll go and put that in my chart to figure out where the potential max and mins are. Moving on down, step 5, we do the second derivative test. So if I look here, this was my first derivative. Do the second derivative. Derivative of the first times the whole second plus the first times the derivative of the second. And if you look, I could factor out an e to the x, and I'm left with x squared plus 2x minus 1 plus 2x plus 2, and I simplified it, and I get that right there. For set the second derivative equal to 0 for points of inflection. This cannot be 0, so it must be this, and I did the quadratic formula, and I got these two ugly decimals, which will eventually go into a chart to figure out where the points of inflection are. So let's do that. Okay, so if you take a look back at step 4, we found that for the first derivative test, we found that there was a horizontal slope at x equal to negative 2.41 and 0.41. So we're going to go and put those values in our chart. So there's the negative 2.41 and there's the 0.41, and then we have to look at all the intervals on either side of that. So we got x less than the negative 2.41, between negative 2.41 and 0.41, and then the other side where x is bigger than the 0.41. So we already know, this is the first thing that I put in, that the slope of the tangent was 0 here and here. That was part of the first derivative test, setting it equal to 0, so we know that it's going to be equal to 0 there. And then you're going to start subbing in values that would be something in this range. So choose negative 10, sub it in, you'll find out that the first derivative would be positive here. Sub in something that is between this range, so if you subbed in 0, you'd get a negative. And then something bigger than 0.41, so maybe positive 10, you'd find out that your slope is positive. That corresponds to, in order, this one would be increasing, decreasing, increasing. When I go from increasing to decreasing, I get a local max, and from decreasing to increasing, I get a local min. And then I go and I actually figure out what that local max would be and what that local min would be. Okay, so my x value is negative 2.41, so I sub that into f of x now. Notice this is f of x, and I get the y value would be 0.43, and on this one I get negative 1.25. You might want to pick up some extra points here, so I just chose 0, negative 3, and 2, and I figured out the corresponding y values. This one, take note, is my y-intercept. And then I go and I do the second derivative test, and I summarize that in a chart. So if you look here, I end up having, if you look back at step 5, my two values where the points of inflection could happen were negative 3.75 and negative 0.27. So I end up with those here, and then the intervals surrounding them, here, here, and here. If you look, take the second derivative. When you sub in a value that is in this range for x, so like negative 10, you end up getting a positive. If you sub in a value in this range, you get a negative. And if you sub in a value for this range, maybe positive 10, you get a positive. That corresponds to concave up to concave down, and then concave down to concave up. We actually figured out those values right here, and that's going to be a point of inflection and a point of inflection. Okay. As I look at this right now, I probably would switch the order just to be consistent with my first derivative test, and I would have probably written them, and swapped them there, just to follow up with the same format that I did in the first derivative test. So that's great. So I figured out some points of inflection. I ended up grabbing just one extra point in addition to the ones that I had up here. And I just figured negative 5 might be a good one. Actually, when I went and did my graph, and you'll see that in another slide or two, that was just an extra point that I wanted to put on my graph, so I came back and I stuck it in right there. Lots of people just list those out in like a 10th step as they need them. It's up to you. Just list them out if you do need them. We get to step 7, so we're looking for the potential for asymptotes. So we let x go to positive infinity for the first one. And if you look, if this goes to positive infinity for x right there, and this one too, overall that's going to be positive infinity. The one that I really liked here was going to negative infinity. Look what happens. If I let this go to negative infinity, this whole term will actually be going to 0. So 0 times a number here is going to be 0 overall. Kind of interesting. So that means I will pick up a horizontal asymptote as x goes to negative infinity right here. And you'll see what that looks like when we get to the graph. Moving on down to step 8. So we look here and we're just looking for any oblique asymptotes, and there aren't going to be any, because this wasn't a rational function. So we're done that step. So now you're going to consolidate all of this into a graph. So what I want you to do is go back and look at all the values that we found in that chart and the extra points, and try and gauge what we're looking at for types of scales. Are we dealing with really big numbers or really small numbers? So once you look at it, you're going to have to decide, oh, let's put on our axes, and then I'm going to skip through some slides that gradually build our graph because it was a lot easier than graphing it on the iPad. So again, think about your scale, and then I'm going to flip ahead and you can see what I chose. So here's what I had. So if you take a look, because my y values weren't huge at all, I decided to go up by 0.2, and I made it so that my graph would be stretched out vertically when you looked at it so that it was easier to graph. And then I stretched out, and every other square on the horizontal axis is 1. So I counted up by halves. Again, just to spread it out a little, it makes it a little more easy to graph it if I can spread it out. So now we're going to try and put the points on here. So if you look back over the last 8 steps, you could have done it in order as you went and built your graph as you were going through it, or you can do it all at the end. I tend to do it a little more at the end. Again, I like to get all the algebra out of the way. The first thing I'd go and plot is the x-intercepts, then I'd go and plot the y-intercepts, then I'd go plot my maximums and minimums, and then I'd go and plot the points of inflection, and then at that point I'd make a judgment call whether I needed some extra points just to determine the general shape. So let's go plot those points. So here we go. I went and actually did all the points in pencil before I scanned these in. So I'm going to circle these. Obviously, you're not going to circle them. So hopefully you paused it and you plotted these. I plotted my x-intercepts first, so that's there and there. I went and plotted my y-intercept next. That was here. I went and did my max and my min in that order. Then I went and did the points of inflection. That's where it's going to turn from concave up to concave down. So here, and I think it was here. And then looking at that, that's quite a few points. Some extra ones that might help. I went and found this one right here. That helped out a lot, and this one here, just to give me my general shape. Now you're going to try and do a nice smooth curve. I have it already done on the next slide. But again, when you're doing this, you want to kind of take note where your maximum is. So I have a maximum here, so that's where my biggest point should be. Here's my minimum. That's where I want my smallest point to be. Here's where it switches from concave up to concave down. So on this side, you want it to be concave down, and on this side, you want it to be concave up. Same with this one right here. And I know it's getting messy, but the next graph is already done, and it looks great. And you connected your curve, or your dots to make the curve, and there you go. It looks awesome. And again, I like the fact that when we were letting x go to negative infinity, we caught a horizontal asymptote way over here, which is really nice. That's the one thing that I'd do. I'd label that horizontal asymptote. I'm going to do it in red. So that was just at y equals 0. And we got a nice, beautiful graph. Hopefully you have no questions. Hopefully that all made sense. And again, this algorithm will work with a bunch of the equations that we've done. As long as you can take the first derivative and second derivative, you can piece out where the minimums are, the maximums are, the points of inflection, and make a nice curve. So I'm going to go through another quick example that's already done for you. You can just sit back and watch the explanation. And again, it has a few asymptotes in it, so you can see how to do those and what format we want. And again, it does the end chart in one big chart, not two separate ones. So if you're so inclined to do it that way, that's totally fine as well. So let's take a peek at that. So right here we have a rational function, kind of similar to what we did last year. Right here. So we're going to go through all the steps. So if we look here, we factor it all, and it doesn't appear that there are any discontinuities that we can get rid of when we could divide out the factors. So had this been like x plus 3, that would have divided out, and we would have had a hole in our graph. So that part's done. When we look at vertical asymptotes, that's where this is going to be equal to 0. So I write that right there, and I get a horizontal asymptote at x equals negative 3. The next step, if y equals 0, then we go through and we solve this when it's 0, and we're picking up our x-intercepts there. I probably would have written right here, for x-intercepts, set y equal to 0. For y-intercepts over here, set x equal to 0, and we get that one. So that's done. Then we go and do the first derivative. So here's us doing the first derivative right here. We set it equal to 0. I would have written for critical values right there. Maybe you want to add that. Set it equal to 0, you get this quadratic. You go through and do the quadratic formula. Super ugly right there, but that's what the x values came out to be. Then we go to step 5 and we do the second derivative test. So if we look here, we end up having what we start with the first derivative. You can see why we simplified it and made it a little easier. You go and you do the quotient rule again and simplify it if you can, because it's a lot easier to deal with simplified form. We set that equal, and I would have written 4 points of inflection right there. We end up getting 0 equals 10. Since that's undefined, there are no points of inflection. So that might make our graph look a little nicer. So when we go through that, we have to list all of the key x values in this scenario. So if you think, in the first derivative test we picked up, and I would have probably put the decimal here instead of the exact form. So I would have put a decimal right there. So we go through, and when we build our chart, everyone was probably fine with the first derivative test that we'd have this value here and this value here. The second derivative test didn't have any points of inflection, but this might surprise people. The x equals -3. Maybe try and guess why that happened. That is where our vertical asymptote was. Okay. I'm going to make a little correction here. So if we look at this right here, this side would be negative. This side would be negative. And this should be undefined. We can switch from having our curve from increasing to decreasing at vertical asymptote or vice versa. So you have to have that in your chart. If you have a vertical asymptote, that is one of the key values that you have to test. And when you get to your second derivative test, you can see that at the asymptote we switched from concave down to concave up. So that's why it had to be in there. Had we left that out, we might not have picked that up. So again, let me summarize that. You have to test all of your key values that you find in the first derivative test, the second derivative test, and if there was any vertical asymptotes. So we did that in this chart. Let's scroll down a little so we can see. And again, we go through. You can pick some extra points to help you out in the different intervals. And I would have probably done that as a decimal because you're going to need to know what it is to go and plot it on your graph anyways. So why are we keeping the exact form? It just makes it a little easier. And I've already done the graph. Actually, I should say Mr. Graph already did the graph because I borrowed his note. And let's finish it up, Step 7 for horizontal asymptotes. We're looking for as x goes to positive or negative infinity, so we have to do both of them. So take a look right here. We simplify, or we rearrange or modify f of x, and as x goes to positive infinity, we'll get 2 over 0, and as x goes to negative infinity, we'll get 2 over 0. So there's no horizontal asymptotes. The reason for that is, if you look, we do have an oblique asymptote. So we go through and we find the oblique asymptote by doing the long division that we saw last semester. We get an oblique asymptote at y equals 2x minus 1. All of this are all the steps that we need to go and complete any sketch that we want. It doesn't matter if it has a trig portion to it, an exponential, logarithmic, or ln. We can do the exact same thing every single time. So that's why you're going to have to memorize this algorithm. We go and put all of that information in, and we get this nice graph. Now remember, last year we did not have enough information to find out what that minimum was right there, or that local maximum was right there. We just didn't have the knowledge, so we picked lots of extra points to help us out. But that's what the result was. We would only estimate it right here, but now with calculus we have the ability to figure out what that value is exactly, which is going to be nice because eventually we're going to get into maximization problems or minimization problems, and we'll need to figure out what that value is exactly. And then you can see at the bottom for the homework, it's all listed out there. We've been really nice. We've told you what the first derivative is for 4e right there and what the second derivative is. So that'll save you having to actually take the derivative for that one. And you can just set them to equal to 0 when you go and do your algorithm for your first and second derivative test. So hopefully this went well. I think Miss Fitz's class is actually watching this video as well because they're going to miss this lesson tomorrow because of the grad breakfast. So welcome to the extra people, and hopefully you guys have a good night. Take it easy.